Welcome to the deep dive. We're kicking off today by looking at something pretty fundamental, the very ground beneath our feet. We often think of it as solid rock, and yeah, it can be, but that rock is frequently covered by a fascinating layer, a veneer, maybe of sediments and soils.
Right.
It's this sort of dynamic interface that we're going to explore today.
That's right. And the surface layer, it's, where the bedrock interacts with the atmosphere, water, life itself. It's a zone of constant change.
Okay.
And understanding how it forms gives us really crucial insights into the landscapes we see, even the history of our planet.
Okay, let's try and get our minds around the power of these processes with a truly epic example. Picture the mighty Nile River.
Okay.
You'd expect it to flow through a valley, right?
Right?
But imagine it flowing over a hidden canyon, a colossal chasm,
Yeah.
1.5 kilometers deep, that's been completely filled with sediment.
Wow, 1.5 kilometers deep.
Yeah, that's on the scale of the Grand Canyon. For a long time, geologists were puzzled over this. How could a river possibly carve a canyon so far below sea level at its mouth?
It seems impossible, doesn't it? What's fascinating here is that the answer lay, well, surprisingly far away, deep in the Mediterranean Sea.
Really?
Yeah, back in the 1970s, scientists drilling into the Mediterranean seafloor made this unexpected discovery. A layer of salt, absolutely staggering, 2 kilometers thick.
2 kilometers of salt.
2 kilometers. This massive salt deposit was a clue, a really big clue, to a dramatic story.
Okay, here's where it gets really interesting then. That much salt, it could only have formed if the entire Mediterranean Sea had, at some point, basically dried up.
Right, likely multiple times over millions of years.
And when the Mediterranean's water level just plummeted, we're talking 1.5 kilometers lower than today,
Unbelievable drop.
the Nile River suddenly had a drastically lower drain to flow into. Imagine the river's erosive power just unleashed, carving down, down, down into that exposed basin floor. It's almost unbelievable.
Exactly. Think of it like a sink emptying. If the drain suddenly drops way down, the water will rush out with much more force, right?
Right.
And it can carve channels as it goes. Once the Mediterranean refilled, the Nile's intense carving slowed, naturally, and the vast canyon it had created just gradually filled up with the gravel, sand, and mud it carried downstream.
Wow.
It's a powerful illustration of how seemingly separate Earth systems are interconnected over these immense timescales.
So this incredible example brings us to the basic stuff, the material that makes up this surface layer, sediment. When we talk about sediment, what exactly are we referring to?
Simply put, sediment is any loose, unconsolidated material found at the Earth's surface.
Okay.
This includes fragments of rocks or minerals that have been broken off larger rocks, things like sand grains, pebbles, even big boulders that have tumbled down a hillside.
Got it.
It also includes mineral crystals that have formed directly from water, like the salt crystals in our Mediterranean example, or, those you might see forming around hot springs. And finally, sediment can be made up of the shells or pieces of shells from living organisms, like you'd find on a beach made of broken seashells.
Okay, so it's all that loose stuff, from mud and sand right up to broken rocks and seashells. Now, how does that solid bedrock we started with actually become all this loose material? What's the process?
That's where weathering comes in. Weathering is the fundamental process that produces sediment. It's the physical and chemical breakdown of pre-existing rocks happening right at the Earth's surface or very close to it, where they're exposed to the elements.
So the seemingly solid rock isn't permanent. It's constantly being attacked, broken down by various forces. And this process creates that surface layer we've been discussing, which is known as the regolith.
Precisely. Regolith is the blanket of loose material, whether it's sediment or soil, that covers the solid bedrock.
Okay.
And the thickness of this blanket can vary enormously. In some places, you might see bedrock sticking right out of the ground, meaning the regolith is, practically non-existent.
Right.
But in other areas, especially in large depressions called sedimentary basins, this layer of sediment and soil can be incredibly thick. We're talking tens of thousands of feet sometimes.
Tens of thousands of feet. Wow. That really puts the scale into perspective. So the goal of our deep dive today is to really understand how this weathering process works to create sediment and how that sediment can eventually be transformed into soil, that life-supporting layer we all depend on. It sounds like this understanding will also be key for when we explore sedimentary rocks in more detail later on.
Absolutely. Understanding these initial processes, the breakdown and modification, it's essential for deciphering the stories held within sedimentary rocks, which are pretty much collections of this sediment that have been compacted and cemented together.
All right, let's really dig into the mechanics of weathering then. Imagine you're passing a brand new road cut. You see this fresh, solid-looking rock.
Right.
Geologists even call it fresh rock.
Yeah,
But then you look around at the natural rock outcrops nearby, and they often look quite different. They might be cracked, discolored, or even crumbling apart. What causes this dramatic change from fresh rock to weathered rock?
You've highlighted a crucial point there. The difference you observe is due to the constant interaction of the rock with the Earth's surface systems. The atmosphere with its gases and moisture, the hydrosphere, all the water, and even the biosphere, all living organisms play a role in altering that fresh rock over time.
So weathering isn't just one single thing. It's a collection of processes that work to break down, corrode, and ultimately transform solid rock into smaller pieces in different chemical forms.
Exactly.
And like our earlier analogy, there are two main categories: physical and chemical weathering. Physical is like mechanically breaking it apart.
Like a plumber snake, yeah.
And chemical weathering is changing its fundamental composition.
Like the drain opener. That's a perfect way to think about it. Physical weathering is the mechanical disintegration of rock into smaller fragments without changing the minerals themselves. Chemical weathering, on the other hand, involves chemical reactions that actually alter or break down the minerals within the rock.
Okay, let's start with the mechanical side, physical weathering, sometimes called mechanical weathering. What are the primary ways this happens? What forces are at play to just physically break the rock apart?
Physical weathering is all about taking intact rock and breaking it down into those unconnected pieces we call clasts, individual grains or chunks of varying sizes.
Clasts, right.
Yeah. Geologists have a whole scale for classifying these clasts based on their diameter, ranging from massive boulders down to microscopic silt and mud particles. It's like a granular hierarchy of broken rock.
Right, so if you took a big rock and smashed it into gravel, and then that gravel got ground down into sand, that would all be physical weathering. What are the actual forces in nature that do this breaking?
Well, one really important process is jointing. Rocks buried deep within the earth are under immense pressure, and they're also hotter than surface rocks.
Makes sense.
When these deeply buried rocks are brought closer to the surface through uplift and erosion, a process called exhumation, the surrounding pressure decreases and the rocks cool. This change in conditions can cause the rock to expand slightly and contract as it cools, generating internal stresses that lead to the formation of natural cracks called joints. Think of it like a subtle sigh of relief from the rock as the pressure is lifted, causing it to fracture.
So it's almost like the rock is breathing out as it gets closer to the surface, and that causes it to crack. These joints, they're just fractures, right? Natural cracks.
Exactly. And these joints can form in different patterns depending on the type of rock and the stresses it experiences. For example, sedimentary rocks often develop sets of planar, vertical joints that intersect the different layers.
Okay.
This causes the rock to break into more or less rectangular blocks. You've probably seen cliffs with that blocky appearance.
I can picture that, yeah. And I've also seen those rounded, almost peeled off layers on granite outcrops. What's causing that? It looks like the rock is shedding layers like an onion.
That's exfoliation. In large bodies of intrusive igneous rock like granite, joints tend to form that are oriented roughly parallel to the exposed rock surface.
Okay.
Over time, these curved sheets of rock break away, giving the outcrop that characteristic dome shape with layers peeling off.
Like exfoliation.
And gravity then plays a role with all this fracturing. Jointed blocks can become unstable and break off, accumulating at the base of slopes as piles of loose, angular rock fragments called talus.
Talus, right. Those piles of rubble.
You often see these steep piles of rubble at the foot of cliffs. Yeah.
Okay, so jointing creates the initial weaknesses, and gravity helps to pull things apart and move them downhill. What other physical forces are at play? I'm thinking about things like ice. Maybe even plants.
Absolutely. Frost wedging is a really powerful agent of physical weathering, especially in climates that experience cycles of freezing and thawing. We all know that water expands when it freezes. Think about what happens if you leave a full water bottle in the freezer.
Yeah, it bursts.
Exactly. When water gets trapped in joints and other cracks in rocks and then freezes, that expansion exerts tremendous outward pressure, literally forcing the cracks to widen and eventually breaking the rock apart. It's very effective in mountainous regions, other areas with freeze-thaw cycles.
That makes perfect sense. The expanding ice acts like a wedge, pushing the rock apart. And I've also seen these rocks, especially near the coast or in deserts, that have these pitted, almost honeycomb-like surfaces. That related to freezing water?
Not directly, no. That's usually caused by salt wedging.
Hull wedging.
Yeah. In arid climates or coastal areas, water containing dissolved salts can seep into pores and small cracks in rocks. As the water evaporates, these salts precipitate out and form crystals.
Okay.
As these salt crystals grow, they exert pressure on the surrounding rock grains, pushing them apart and causing the rock to disintegrate. That honeycomb texture you mentioned is a telltale sign of salt wedging in action.
Interesting. So it's the growth of the salt crystals, not the expansion of water, that's doing the work there. What about those tree roots that can crack sidewalks? Do they have a similar effect on rocks?
They certainly do. Root wedging is another significant physical weathering process, particularly in areas with vegetation.
Yeah.
As tree roots grow, they naturally seek out any available space, including existing joints and cracks in rocks. As the roots thicken and expand, they act like natural wedges, exerting immense pressure that can widen the cracks and eventually break even quite large rocks apart.
Just like the sidewalk.
You're right, it's the same principle that causes them to lift and crack sidewalks.
And I've heard that even just changes in temperature can cause rocks to break down. How does that work? It seems like a subtle force.
It is subtle but relentless. That's thermal expansion and contraction. When a rock is heated, it expands slightly, and when it cools, it contracts.
Okay.
While these changes in size might seem minuscule, repeated cycles of heating and cooling can create stress within the rock. For example, during an intense forest fire, the outer layers of a rock can heat up rapidly and expand, then cool and contract quickly. This differential expansion and contraction can cause the outer layers to fracture and break off in sheet-like pieces. It's a type of thermal fracturing or exfoliation on a smaller scale. Even the daily cycle of the sun heating dark-colored rocks in a desert environment can, over long periods, lead to fracturing due to these repeated stresses.
So it's like the rock is getting fatigued from the constant expansion and contraction until it eventually gives way. And I guess even living creatures, including us humans, can play a role in physically breaking down rocks.
Absolutely. Burrowing animals, from tiny earthworms turning over soil and moving small rock fragments to larger animals like gophers, they all contribute to physically disturbing and breaking down rock near the surface, exposing new surfaces to further weathering. And humans. Well, we are, without a doubt, a major agent of physical weathering today. Think about all the earth-moving activities we undertake. Quarrying for building materials, excavating foundations, mining, or even just constructing roads. All of these involve breaking, crushing, and moving vast amounts of rock.
It's really amazing to consider all the different ways these seemingly solid rocks are being physically broken down into smaller pieces. Now let's shift our focus to the drain opener, chemical weathering. How does this work to actually change the composition of the rock?
Right. Chemical weathering involves actual chemical reactions that alter or decompose the minerals that make up the rock. These reactions occur when the rock comes into contact with water solutions or the air. There are several key types.
Okay, what's the first chemical attack in nature's toolkit? What's the primary way rocks get chemically altered?
One fundamental process is dissolution. This is where minerals in the rock actually dissolve into ions that become surrounded by water molecules.
Like salt in water.
Exactly. Think of salt or sugar disappearing when you stir it into water. Different minerals have different solubilities. For example, salts like halite dissolve very easily, while silicate minerals like quartz are much more resistant.
Okay.
And the acidity of the water plays a significant role here too. Carbonate minerals like calcite, which is the main component of limestone and marble, dissolve much more readily in acidic water.
And where does this naturally acidic water come from? It's not like it's raining vinegar, right?
That's right. Rainwater is naturally slightly acidic because it dissolves carbon dioxide from the atmosphere, forming a weak acid called carbonic acid.
Ah, carbonic acid.
As this slightly acidic rainwater seeps down through the soil, it can react with decaying organic matter, further increasing its acidity. This is why regions with abundant limestone and marble bedrock often develop extensive underground cave systems through this process of dissolution.
Wow.
The slightly acidic groundwater just slowly dissolves away the rock over vast stretches of time.
So those incredible caverns are essentially formed by this slow chemical dissolving of the rock by slightly acidic water. Amazing.
Yeah.
What's the next key type of chemical weathering?
Another very important one is hydrolysis. This involves water chemically reacting with minerals and breaking them down to form entirely different minerals. The term lysis essentially means to loosen or to break down.
Electrolysis, okay.
A common example is the weathering of potassium feldspar. a very abundant mineral in rocks like granite.
Right, feldspar.
When potassium feldspar reacts with slightly acidic water, it undergoes hydrolysis and transforms into kaolinite, which is a type of clay mineral, along with some dissolved ions.
Feldspar turns into clay.
Many other silicate minerals, which are the most common type of mineral in the Earth's crust, including minerals like amphibole, pyroxene, mica, and olivine, also undergo hydrolysis, although often at different rates, eventually transforming into various types of clay minerals. Interestingly, the mineral quartz also undergoes hydrolysis, but at such an extremely slow rate that it often survives weathering while the other minerals in the same rock have been completely altered.
So hydrolysis is not just breaking the rock into smaller pieces, it's fundamentally changing the mineral composition. Feldspar to clay, for example. What about that reddish-brown color we often see on weathered rocks? Is that another form of chemical weathering at work?
Yes, that's typically due to oxidation.
Oxidation, like rusting.
Exactly. In chemistry, oxidation is the process where an element loses electrons, and this often happens when elements combine with oxygen. The rusting of iron is the classic example.
Right.
In rocks, minerals that contain iron, such as biotite or pyrite, can undergo oxidation reactions, transforming the iron within them into weaker, rusty brown mixtures of iron oxide and iron hydroxide minerals. This oxidation often weakens the overall rock structure and makes it more susceptible to physical weathering as well.
So oxidation is like the rock rusting away when it's exposed to oxygen and water. Are there any other significant chemical weathering processes we should know about?
One more important one to mention is hydration. This is where water molecules are absorbed into the crystal structure of certain minerals, causing them to expand.
Expand.
Yeah. Some types of clay minerals, for instance, can significantly increase in volume when they become hydrated. This expansion can create internal stresses within the rock, weakening its structure and making it more prone to physical breakdown.
So the rock is almost swelling up and fracturing from the inside due to absorbing water. Now, we've talked about these different minerals and these various chemical weathering processes. Do all minerals weather at the same rate when exposed to these conditions, or are some tougher than others?
Oh, absolutely not. Different minerals have vastly different degrees of stability at the Earth's surface. For example, minerals that crystallize at higher temperatures and pressures deep within the Earth.
Like from Bowen's reaction series.
Exactly, like described by Bowen's reaction series, tend to be less stable when exposed to the cooler temperatures and different chemical conditions found at the surface.
Right.
Conversely, minerals that are themselves the products of weathering, like hematite and iron oxide, tend to be very stable under surface conditions.
That makes sense. The minerals that formed in a very different environment are trying to reach a new equilibrium, and some are more resistant to that change than others. What about general types of minerals? Do silicate minerals tend to weather in a particular way compared to, say, carbonate minerals?
Generally speaking, yes. Mafific minerals, which are rich in iron and magnesium, tend to weather primarily through oxidation and hydrolysis.
Okay.
Felsic minerals, which are richer in silicon and aluminum, are more susceptible to hydrolysis. Carbonate and salt minerals, as we discussed, are particularly vulnerable to dissolution.
Right.
And oxide minerals, like quartz, tend to be very resistant to chemical weathering, although they aren't completely immune over very, very long timescales.
And that perfectly explains why beaches are often composed mainly of quartz sand, because the quartz is so chemically resilient that it survives the breakdown of all the other minerals in the original rocks.
Exactly. Quartz, with its strong three-dimensional network of silicon-oxygen bonds, is exceptionally stable at the Earth's surface. When a rock like granite, which contains quartz, mica, and feldspar, undergoes chemical weathering, the mica and feldspar often alter to clay minerals through hydrolysis, leaving behind the relatively inert quartz grains that eventually become the sand we see on beaches.
We've been focusing a lot on the purely chemical reactions, but I know that living things also interact with rocks in significant ways.
Yeah.
How do plants, fungi, and microbes contribute to this process of weathering?
You're right to bring that up. Biological weathering is a significant factor, and it often bridges the gap between physical and chemical processes.
How so?
Well, plant roots, as we discussed, can physically wedge rocks apart, but they also release organic acids as they grow,
Acids.
which can help to dissolve minerals in the surrounding rock as they seek out nutrients. Similarly, fungi and lichens, which often grow on bare rock surfaces, also secrete organic acids that contribute to the chemical breakdown of the minerals beneath them.
Okay.
And incredibly, some microbes, like certain types of bacteria and archaea, can directly extract energy from the chemical bonds within minerals, essentially breaking down the mineral structure at a molecular level to fuel their metabolic processes.
Wow, so they're literally eating the rock.
In a way, yes. It's a fascinating interplay between the living and non-living components of the Earth system.
So even these tiny organisms are playing a role in breaking down the very rocks they live on, often by releasing chemicals that attack the minerals. Now, we've looked at physical and chemical weathering somewhat separately, but I imagine they don't operate in isolation in the real world. How do they interact and influence each other?
They are indeed very much interconnected and often work together in a synergistic way, each enhancing the effects of the other. Physical weathering, by fracturing a large rock mass into smaller pieces, dramatically increases the overall surface area of the rock exposed to the environment.
Right, more surface to attack.
Exactly. Think of breaking a large block into many smaller fragments. You suddenly have a much greater total surface area. This increased surface area provides far more opportunities for chemical weathering reactions to occur. The chemical agents have more points of contact.
So by physically cracking a rock open, you're giving the chemical weathering agents more places to get in and do their work.
Yeah.
What about the other way around? How does chemical weathering help physical weathering?
Chemical weathering weakens the structural integrity of the rock. By dissolving away the minerals that act as natural cement holding the rock together, or by transforming hard, resistant minerals into softer, more easily crumbled ones like clay, or even by causing minerals to expand through hydration, chemical weathering makes the rock far more susceptible to physical breakdown.
I see.
A block of granite that has undergone significant chemical weathering will be much more likely to fracture and crumble under physical stress than a fresh, unweathered block.
It's a real team effort in breaking down the bedrock. I've also noticed that weathered rocks often have rounded edges and corners, even if they started out as sharp, angular blocks. Is there a specific reason for this rounding effect?
Yes, that's a result of spheroidal weathering.
Spheroidal weathering.
Imagine a rectangular block of rock. The corners are exposed to weathering from three sides, right?
Right.
The edges from two sides, while the flat faces are only exposed from one side. Because of this greater exposure, the corners and edges tend to weather more rapidly than the flat faces.
Oh, makes sense.
Over time, this differential weathering causes the sharp edges and corners to become progressively rounded. In homogeneous rocks like granite, this process can eventually lead to the formation of almost perfectly spherical boulders. Sometimes, exfoliation can even occur on these rounded boulders, with concentric layers peeling off.
So it's like the rock is being slowly sculpted by the weathering processes, with the more exposed parts wearing away faster. Now, the landscapes we see are made up of many different types of rocks. Does the type of rock present in an area significantly affect how it weathers and the landforms that result?
Absolutely. Different types of rocks have different mineral compositions and therefore exhibit varying degrees of resistance to both physical and chemical weathering. This leads to what we call differential weathering.
Differential weathering, okay.
In an outcrop that contains alternating layers of strong, resistant rock and weaker, less resistant rock, the weaker layers will naturally weather away more quickly than the stronger layers.
Right.
This can result in the formation of distinctive landforms, such as those stair-step or sawtooth-shaped cliffs you see in some regions, where the more resistant layers protrude as ledges or pap rocks.
I can picture that like a layered cake, where some layers are being eaten away much faster than others, leaving behind the tougher parts. You mentioned graveyards earlier as an example. How do old headstones in a cemetery illustrate this idea of differential weathering?
Graveyards actually provide an excellent real-world illustration of differential weathering. Headstones are often made from different types of rock. The made of granite, which is rich in the very resistant mineral quartz, tend to retain their inscriptions and sharp edges for centuries, showing very little sign of weathering.
Okay.
In contrast, headstones made of marble, which is composed primarily of calcite, are much more susceptible to chemical weathering, particularly dissolution by slightly acidic rainwater.
The calcite dissolves.
Exactly. Over just a few decades, the inscriptions on a marble headstone can become significantly blurred and the edges rounded, sometimes even to the point of becoming illegible. It's a stark visual demonstration of how different rock types respond to the same weathering environment.
That's a really clear and relatable example. We've talked a lot about how weathering creates sediment by breaking down rocks. What about erosion? How does that process fit into this whole picture of shaping the Earth's surface?
Right. Weathering is the essential first step. It's the process that breaks down the solid rock, creating the loose sediment. Erosion is then the process that picks up and transports that weathered material.
The moving part.
Yeah, the movement. Whether it's moved by wind, flowing water in rivers, glaciers, gravity pulling material downhill, wave action along coastlines, or even the dissolving action of water on soluble rocks like limestone. Without weathering to create the loose particles, there wouldn't be much for the agents of erosion to move.
I see.
So weathering is the crucial precursor that makes erosion possible and allows for the redistribution of earth materials across the landscape.
Okay, so weathering creates the raw ingredients, the loose sediment, and erosion is the force that moves it around. Now, we've spent a lot of time talking about sediment, but right at the beginning we also mentioned soil. How does this loose sediment actually transform into soil? It's clearly more than just broken up rock, right? It's the stuff that plants grow in.
That's a crucial distinction, yeah. Soil is far more than just weathered rock or sediment. It's a complex, dynamic material that has been modified over time through physical and chemical interactions with organic matter derived from living organisms and the percolation of rainwater.
Yeah.
It's a vital natural resource that supports almost all terrestrial life on our planet, forming the foundation for agriculture, forestry, and countless ecosystems.
So what are the key processes involved in the development of soil from this initial sediment? What are the essential ingredients and actions?
There are three main categories of processes that contribute to soil formation. First, you have the continued production of mineral debris through the ongoing physical and chemical weathering of the underlying rock or sediment.
Right, the mineral base.
That provides the basic mineral framework of the soil. Second is the interaction with water. As rainwater infiltrates down through the loose material, it carries dissolved ions and very fine clay particles downward in a process called leaching.
Leaching, moving stuff down.
Exactly. Deeper down in the soil profile, in what's known as the zone of accumulation, these leached ions can precipitate out of solution, forming new minerals, and the clay particles can accumulate, altering the soil's texture and composition.
Okay, accumulation below leaching.
And third, and perhaps most importantly for the development of true soil, is the interaction with living organisms. Soil is a habitat for an incredibly diverse range of life, from microscopic bacteria and fungi to plant roots and larger animals like earthworms and insects. These organisms contribute in many ways. They absorb nutrients, they leave behind waste products, they secrete acids that can further weather minerals, they physically churn and mix the soil, improving its structure and aeration.
Mixing it all up.
And when they die and decompose, they contribute organic matter, which we call humus. Humus is that dark, rich material that's so characteristic of fertile topsoil.
Humus, that dark, crumbly stuff that makes healthy soil so productive. So it's this ongoing combination of broken down rock, the movement of water-carrying dissolved materials, and the constant activity and decay of living things that ultimately creates soil. And I know that if you dig down into the soil, you often see distinct layers. What are those different layers?
Right. Those distinct, roughly parallel layers you see when you dig a soil pit are called soil horizons.
Horizon.
And the entire vertical sequence of these horizons is known as a soil profile. These horizons develop because the various soil-forming processes operate at different depths. Let's consider a typical soil formed under a temperate forest as an example.
Okay.
At the very top, you might find the O horizon, which is primarily composed of organic matter, decaying leaves, twigs, other plant debris.
O for organic. Makes sense.
Below that is the A horizon, often called topsoil, which is a mixture of humus and mineral grains derived from the underlying weathered material. The A horizon is a zone of significant leaching.
A is topsoil. Leaching happens there.
Sometimes you'll find an E horizon just below the A. This is a transitional layer that has undergone substantial leaching, losing both minerals and organic matter, giving it a lighter color.
E for alluviated, maybe? Leached out?
It's exactly. Alluviated is the technical term. Below the E is the B horizon, or subsoil, which is a zone of accumulation. Here, ions and clay particles that were leached from the horizons above have precipitated out or collected.
B, where things build up.
Precisely. Finally, at the bottom is the C horizon, which consists of weathered parent material, the original rock or sediment that hasn't yet been significantly altered by leaching or accumulation. The C horizon gradually transitions into the unweathered bedrock or original sediment.
C is the weathered parent material.
Yeah. And it's important to remember that the O, A, and E horizons are generally considered the zones of leaching, while the B horizon is the primary zone of accumulation.
Okay, that structure makes sense. Now, If you travel to different parts of the world, you encounter vastly different types of soil. What are the main factors that control the specific characteristics of a soil in a given location? Its composition, its thickness, its texture, and so on.
Several key environmental factors exert a strong influence on soil development. Climate is a major one.
Climate, okay. How so?
The amount and distribution of rainfall and the prevailing temperatures directly affect the rates of both chemical and physical weathering, as well as the intensity of leaching and the amount of biological activity. Warm, wet climates tend to promote faster chemical weathering and more extensive leaching.
Right. What else?
The nature of the underlying substrate, or parent material, is also crucial. A soil that develops on volcanic ash, for instance, will have a different chemical composition and physical properties than a soil that forms on granite bedrock or sandy sediment.
So what it starts from matters.
Definitely. Also, soils tend to develop more quickly on loose, unconsolidated material than on hard, solid bedrock.
Makes sense. Easier to work with.
The steepness of the local slope is another important factor. Thick, well-developed soils tend to accumulate on relatively flat or gently sloping land, while erosion on steep slopes can prevent significant soil accumulation, resulting in thinner, less developed soils.
Slope matters for thickness.
The level of wetness, meaning the proximity to groundwater, can also significantly influence weathering rates and the accumulation of organic matter. And finally, time is a critical factor. Older soils have generally had more time to undergo weathering, leaching, and biological modification, and thus tend to be thicker and exhibit more distinct horizons than younger soils.
How fast does soil form?
The rate of soil formation can vary greatly depending on these factors, but in temperate regions, it's a relatively slow process, often on the order of millimeters per year, maybe less.
Millimeters per year, that is slow.
And one more factor. The type of vegetation that grows in an area also plays a significant role, influencing the amount and type of organic matter added to the soil, as well as affecting erosion rates through their root systems.
So a thin, sandy soil in a dry desert environment is going to be very different from a thick, dark, organic-rich soil in a humid forest. It's a complex interplay of all these different environmental controls. I noticed in the source material that there are different ways to classify soils. Can you briefly tell us a bit about how soil scientists categorize these diverse soil types?
Yeah, soil classification is indeed a complex field, and soil scientists have developed various systems to organize the wide array of soil types found around the world. In the United States, a comprehensive system is the U.S. Comprehensive Soil Classification System, which recognizes 12 major soil orders based on their key physical and chemical properties and the dominant soil-forming processes that have shaped them.
12 orders.
12 major ones, yes. Canada, for example, uses a different system that is particularly well-suited to the colder climates found in much of that country.
Okay. Can you give us a couple of specific examples of these soil orders and how they relate to the climate where they are typically found? It would help to make this more concrete.
Certainly. In arid and semi-arid regions where there is very little rainfall, you typically find soils belonging to the order aridesols.
Aridesols. Arid. Makes sense.
Because of the lack of water, these soils generally have very little organic matter and often lack a significant O horizon. Instead, they are characterized by the accumulation of soluble minerals, such as calcite, in the B horizon.
Accumulation even with low rain.
Yeah, due to the low amount of downward water movement and the upward movement of water through capillary action, these dissolved minerals can precipitate out, sometimes forming a hard calcium carbonate-rich layer known as caliche or calcrete.
Caliche, okay. What about a wetter place?
In contrast, in temperate forest environments that experience moderate rainfall, a common soil order is alphasol. These soils typically have a well-developed O horizon and exhibit a clear accumulation of leached materials, such as clay, in their B horizon, indicating a moderate degree of weathering and leaching.
Alphasols in temperate forests.
Got it.
And tropical.
Then, if we move to tropical regions with very high temperatures and abundant rainfall, we often find soils classified as oxasols.
Oxasols. Lots of oxides.
That's right. In these environments, intense chemical weathering and leaching occur over long periods, resulting in soils that are deeply weathered and have lost most of their soluble minerals. The A horizon in oxasols is often rich in very stable iron and aluminum oxides and hydroxides, which can give them a characteristic reddish color.
Very red soils.
Yes. In many oxasols, the extreme weathering has been so thorough that a distinct B horizon doesn't even fully develop. A specific type of oxasol that is particularly rich in iron oxides and can harden into a brick-like material when exposed to air in a dry season is called laterite. Yeah, which in some regions has historically been used as a building material, believe it or not.
Wow, building bricks from soil. It's really striking how these vastly different climatic conditions lead to the formation of such distinct soil types with their own unique characteristics. It truly highlights the powerful influence of those environmental controls we discussed. Now, soil seems like such a fundamental resource for life. Are there significant threats to our soils that we should be concerned about?
Absolutely. Soil formation, as we've established, is generally a very slow process. So fertile topsoil should definitely be considered a precious and, frankly, non-renewable natural resource on human timescales.
Non-renewable, that's a serious point.
It is. Unfortunately, various human activities are leading to significant rates of soil destruction and degradation around the world. Two of the most widespread and critical issues are nutrient removal and soil erosion.
Nutrient removal that makes intuitive sense. When we harvest crops, we're essentially taking away the nutrients that the plants have absorbed from the soil. If that organic matter and those nutrients aren't adequately returned to the soil as humus, it can become progressively depleted, less fertile over time.
Exactly. While the application of synthetic fertilizers can help to replace some of these lost nutrients, this can be costly and can also have negative environmental consequences if not managed properly.
Right.
The clearing of rainforests provides a particularly stark example of the impact of nutrient removal. While rainforests have a large amount of biomass and rapid nutrient cycling, much of the nutrient wealth is stored in the vegetation itself, not so much in the soil.
It's in the plants.
Primarily. When the forest is cleared and burned, the organic matter is lost rapidly, and the underlying soils, which are often those oxisols that are already heavily leached and relatively infertile, can quickly become depleted of the remaining nutrients, sometimes leading to the formation of that hardened, infertile laterite we mentioned.
So clearing rainforests can lead to basically useless soil very quickly.
Devastatingly quickly.
And then there's the issue of soil erosion, the physical removal of topsoil by the action of wind and flowing water. How does this happen, and what are some of the ways that human activities can exacerbate this natural process?
Well, when natural plant cover, like forests or grasslands, is removed through deforestation, agricultural practices like continuous plowing or overgrazing, the soil surface is left exposed and vulnerable.
Bare soil.
Exactly. The direct impact of raindrops on bare soil can break down soil aggregates, and the force of flowing water can then easily wash away the loosened soil particles. Similarly, exposed, dry soil is highly susceptible to being picked up and transported by wind, leading to dust storms.
Like the Dust Bowl.
Precisely. Human activities often significantly increase the rate of soil erosion, sometimes by as much as tenfold to 100-fold compared to natural rates. This accelerated erosion far exceeds the typically slow rate of soil formation, leading to a net loss of valuable topsoil. You've probably seen examples: muddy runoff after heavy rain, gullies forming on bare slopes.
Yeah, definitely.
The Dust Bowl in the United States during the 1930s is a dramatic historical example of the devastating consequences of widespread wind erosion following the removal of native prairie grasses and a prolonged drought.
That's a really sobering reminder of the critical importance of soil conservation and sustainable land management practices. Are there any other significant threats to the overall health and quality of our soils that we should be aware of?
Yes, unfortunately, there are several other important threats. The overuse or improper application of synthetic fertilizers, pesticides, and herbicides can lead to chemical contamination of soils, harming beneficial soil organisms and potentially entering the food chain. Also, in arid and semi-arid regions, excessive or poorly managed irrigation can lead to a process called salinization.
Salinization. Too much salt.
Exactly. Salts dissolved in the irrigation water accumulate in the topsoil as the water evaporates, eventually reaching levels that are toxic to many plants.
Okay.
Additionally, activities like industrial spills and improper waste disposal can introduce toxic pollutants into the soil, rendering it unusable for agriculture and posing risks to human and environmental health.
So, lots of threats.
Yes. Thankfully, there is a growing global awareness of the fragility and importance of soil, and many efforts are underway to promote soil conservation, sustainable agriculture, and remediation of contaminated soils.
It's definitely a crucial issue that deserves much more attention.
Yeah.
Well, we certainly covered a tremendous amount of ground in this deep dive, from the initial weathering of bedrock to the intricate development of soil and the serious threats it currently faces.
We have indeed. To summarize the key concepts, sediment is any loose, unconsolidated material formed at the Earth's surface. Weathering, encompassing both physical and chemical breakdown, is the primary process responsible for creating this sediment.
Right.
Soil, on the other hand, develops over time as the sediment or even weathered bedrock undergoes complex interactions with water and living organisms, leading to the formation of distinct soil horizons.
Mm-hmm.
The specific characteristics of any given soil are strongly influenced by the parent material it formed from, the prevailing climate, the topography, the activity of living organisms, and the amount of time the soil-forming processes have been acting.
And we've also underscored just how absolutely vital healthy soil is as the fundamental basis for agriculture and terrestrial ecosystems, as well as the significant threats it faces from human activities such as erosion, nutrient depletion, and contamination.
Precisely. This understanding of sediments and soils is not only fundamental to the field of geology, but also has profound and far-reaching implications for our environment, our ability to produce food, and ultimately, our long-term sustainability on this planet.
So as you go about your day, I encourage you, take a moment to really look at the ground beneath your feet with maybe a new perspective, considering the often incredibly slow pace of natural soil formation in many areas and the potentially rapid rates of erosion we can sometimes witness. Well, what are the long-term implications for global food security and how we utilize and manage our precious land resources?
That's a huge question.
It's definitely a thought-provoking question to ponder. Hopefully this deep dive has given you a new and deeper appreciation for the ongoing processes that are constantly shaping the very surface of our planet and the vital role that seemingly simple dirt plays in sustaining life as we know it. Thanks for joining us on this deep dive.